So hi everyone, hello. Am I audible? Okay. So hello everyone, good evening, very good evening. So let us start today's class. So today what I'll be doing, I'll be going through the week 2 assignment, and if time permits I'll be just touching some of the some other important concepts, and by the meantime, like also try to answer some of the questions and some of the topics which I feel needs a little bit of more discussion. So but at first I'll be starting by solving previous year's week 2 assignment. Okay, fine. And in the meantime, everyone, please kindly switch off your microphones. Okay. Camera on. Okay, fine. So first of all, the first question is, they have asked us to select true or false for the following statements. Uh, first, first one is given as, it is given that beta NMOS is less than beta PMOS for the same physical parameters WL TOX. Okay. So what is beta N? So basically, if you see the current equation of a transistor, it is mu Cox W by L VGS minus VT into VDS minus VDS square by 2, okay, in linear region. So now this term mu Cox W by L, here it is taken as beta. Okay, don't confuse it with the current gain of a BJT. No, it's different beta. In many places it is written as kn or kp. Okay, in many books it is mentioned as kn or kp. Out of this out of this term is called the aspect ratio. This W by L is also called the aspect ratio of a transistor. Why? If you closely see this mu, this term, this mu and Cox, these are fixed for a given MOSFET. Once you have fabricated the device, it is fixed for the MOSFET. Not even before fabrication also, for given technology, mu and Cox are generally fixed until and unless you change the doping and all, or oxide thickness and all. You cannot change this mu and Cox. However, this term, this W by L term, it is in control of the circuit designer. We can change the W and L values to get different values of current or capacitance as per our requirement. Even in digital design, L is also fixed. We generally take L as the minimum value, and we generally tweak the width W of the MOSFET to get the desired results. Okay, so here by beta they mean mu Cox W by L. Okay, so it is given that they are saying that whether beta NMOS is less than beta PMOS or not. Now let us see what happens. So it is given they have the same physical parameters, therefore W of NMOS is given as equal to W of PMOS, L of NMOS is given as L of PMOS, and Tox of NMOS is given as Tox of PMOS. Now we know capacitance equals to A epsilon by D. Okay, D here is Tox. So if I take normalized capacitance per unit area, it will be epsilon by Tox. Now as Tox n equals to Tox p, therefore I can write that Cox of n will also be equals to Cox of p. Okay, because Tox of n is equals to Tox of p, therefore Cox of n would also be equal to Cox of p. Let me write it epsilon by Tox n equal to epsilon by Tox of p. Okay, so okay, so Cox, so I got these conditions, I got these three conditions and this condition. Now we know for MOSFETs generally mobility of NMOS is generally almost twice as mobility of PMOS. Okay, so mu n is almost twice as mu p. Therefore I can say my beta n would be mu n Cox n W by L of NMOS. Okay, and beta p would be equals to mu p Cox p W by L of PMOS. Now, as mu n is twice of mu p and Cox and Cox p W L all are same, I can simply write beta n would be equals to if I can get some space, therefore beta n would be equals to twice mu p and Cox n would be equals to Cox p and W by L is equals to W by of p. It is equals to twice of beta p. Therefore, beta n is twice of beta p. Therefore, beta n is beta p. Therefore, the first statement is false. This first statement is false. Okay. Hope it is clear, right? If you feel that I am going too fast, I have a habit of going too fast, just tell me, I will go slow. Okay. So now the second question is, the second statement is both PMOS and NMOS devices are required in an inverter design. Now I would like to throw this question open to you. What is your view that whether I need both PMOS or NMOS device to make an inverter design? Or I can design it using a single PMOS or a single NMOS also without using the other, the complementary device. So if anyone can answer, let's make this a little bit of interactive session. So it's open to you. Anyone? Think for a minute or two. Yes, Jai Surya, you can go ahead. Both are required. Okay. Why you are saying that? Like for example, sir must have shown that one is required to pull down the output load capacitance to ground and one is required to pull up to VDD, right? So I need both PMOS and NMOS. That's what you are saying, right, Jay? Yes. Anyone else wants to tell their views or any ideas? Anyone? Okay. Now let's see. Okay. I've got a bit of space. Okay. Let me draw it here. Okay. See. This is the circuit that we are calling as inverter. Okay, right? It is an inverter. You will give such kind of voltage, you will get this kind of voltage. For low, you will get high, and for high, you will get low, right? For low logic, you will get high logic. For high logic input, you will get low logic output. That's fine. But what if I draw this circuit? Will it act as an inverter? Anyone? Will it act as an inverter? Why? See what happens. Okay, can you mute yourself kindly, Bharat? Otherwise, just give me a minute. Can I pin myself? Otherwise, everyone's screen is being shown. Okay, pinned. Fine. Fine. Okay, see. Here, when the input is low, my NMOS will be turned off, right? On that time, my output will be VDD. Okay, my output will be VDD, correct? Or there might be some small drop due to this IR, but generally with time it will go to VDD. Output will go to VDD when input is low. But when my input is high, what will happen? This NMOS will turn on, so it will try to pull this the output capacitance, the load capacitance, it would try to pull it down to 0. It would try to, it would, what it would do? It would try to pull it down to ground. Okay, but but this is a resistor, right? So it will try to charge it. Okay, so what will happen when my input is high? I'll still get this kind of characteristic, but it will not reach 0. It will not reach 0. Okay, I'll get such kind of characteristic. For a properly designed, I'll get such kind of characteristic. And this voltage will be called as V output low. You will be studying, I think, in future classes, V input low, V output low. So my V output low would not go to ground. Okay, my V input, my V output. So there will be a competition. There will be a struggle, a competition between this resistor and this transistor. Okay, it will try to charge this output load CL to VDD. This should try to discharge it. It would try to discharge it, but generally the strength of this MOSFET, if it is greater, generally it is greater, my V out would be low, and when V out, this transistor is made much more stronger, the V output low can be made very small. Okay, but such kind of circuits, it still works as an inverter. So we can also make inverter using a single transistor. A similar case for PMOS also. Okay, I can use using a single PMOS also, I can design an inverter. Okay, so and anything else? Okay, so this kind of things are generally done. There are some other logics. This circuit that you have studied, it is called an complementary MOS circuit, CMOS circuit. Whatever is there in the pull down network, whatever is there in the pull down, this is the pull down network. Whatever is there in the pull down network, the pull up network is generally complement of this one. Okay, so if my pull down network is of the form of NAND architecture, the pull up will be in the form of NOR architecture. Okay, this is called a complementary circuit. But in other kind of logics, you can also design an inverter using a single transistor. Got my point? So basically the answer that was given here was true, but the answer that previous year they have accepted was true, but it will not be true, it will be false. Maybe the person who has solved it, he has made some mistake. You can also design inverters using other logics, using a single NMOS or a single PMOS. Okay, so it will be false. Any question here? Anyone? Okay, let's move forward then. Okay, fine. So the next statement is for V output greater than V input minus V threshold for an NMOS device of an inverter operates in the linear region. Now let's see in which region it is operating actually. Okay, so given, we have been given what? We have been given an NMOS. Okay, so let me call this as V output and let me call it as V input. So it is given V output is greater than V input minus V threshold of NMOS, right? It is only given V output is greater than V input minus V threshold of NMOS. Now what is V output here? V output here is V drain. Okay, so basically this is my drain, this is my source, and this is my gate. So V output is V drain. V drain is greater than V input. V input here is Vg. Okay, and V threshold is Vth, and simply. Okay, so I can simply say, if I subtract source from both the sides, it would be Vd minus Vs greater than Vg minus Vs minus Vth of n. So Vds is greater than Vgs minus Vth of n. So which region is it is in? It is in saturation region. Got my point? So my device will not be in linear region, rather it would be in saturation region. So it would be, so it would be false. So the correct answer is false, false, false. In class it is given as previously it was accepted as false true false, but it would be false false false. Okay, because we can design an inverter using a single PMOS or using a single type of MOS also, using using PMOS or NMOS only. Okay, so like if you want to further clarify it, just write a mail to your professor, Professor Madhav Rao, that sir, you, in the previous year you have discussed it like this, but this is also possible. So it would be nice to hear his comments also about this thing. This is my comment. Okay, because we can design inverters, there are many other logics of designing an inverter. Maybe as he was talking about CMOS circuits, that's why he has given this answer. But we can design inverters using other kinds of logic also, without using only using a single kind of MOSFET structure. Okay, so next question. Okay, it has been told that the four regions A, B, D and E are marked in the figure, which shows the DC transfer characteristic of a CMOS inverter. Select the correct working modes of the CMOS devices in region B. Okay, so let us first look into in which region our PMOS and NMOSs are in which modes of operation. Okay, let us look into it. And here space is less. So question number 2 and question number 3 are almost same. In question number 2 they have asked about region B, and in question number 3 they have asked about region E. So let me take up this space. Okay, see, here one region is actually they have not shown, some region C here in the middle. Okay, here it has not been shown, maybe he will be talking about it later on, but I'll be talking about you, this is in this region. We'll be seeing what happens here also. Okay, so that your concept gets clear. Now let's start with region of operation A. In region A, what are my transistors in which situation? Okay, in region A you can see, if this is my CMOS circuit, this is my PMOS, this is my NMOS, and this is V in, this is V out. At this region my V in is very small, V in is very small, near 0 volt. Let us consider 0 volt only for this case. So if V in is 0 volt, for NMOS transistor my VGS would be 0 minus 0 0. Okay, my VGS would be 0. So VGS is less than VT. So NMOS is in off condition, right? Cut off condition. And PMOS, so for PMOS it would be 0 minus VDD. So PMOS would be VGS would be 0 minus VDD, which is minus VDD. So VSG would be plus VDD. So my PMOS is in on condition. It is in linear condition. Okay. Now how it is in linear condition? Let us see that also. What is its VDS? V source is V out, which is for 0 volt my VDD would be, say it is a 5 volt technology, say VDD would be V output would be 5 volts. Okay, so this is my source, this is my drain. So my VDS would be 5 minus 5, it is 0 volt. Okay, so VDS is less than VGS minus VT, so it is in linear region, right? So my this region is in this region, A region, my PMOS is in linear region, NMOS is in saturation region, in cutoff region. Are you guys with me? Is it clear? If any issues or if any question arises, I am ready to answer it. Okay, so now let's move to region of operation B. That is, my VDD is slightly greater than VT, or the VDD my voltage is greater than VT of NMOS. Now see in which region of operation my transistors are. Okay, so for region B, say my V input is something around VTN plus Vx, let me call Vx is a small number, so it is VTN plus Vx. So for NMOS, what will be my VGS? what will be my VGS? So VG is, say, VG is VT plus something, okay, it's okay. So my VGS would be sorry, VGS minus VT would be VT plus Vx minus Vt, which is equals to Vx, which is greater than 0. So it would be in which region? On either linear or saturation, which we will see by checking the VDS of this. And its VDS would be equals to its V drain would be something near 5 volt, not 5 volt. You can see the voltage is decreasing here. So let us assume 5 volt only, 5 volt or lower than 5 volt. So VDS would be VDD minus V source. V source is here 0 volt. V source is here 0 volt, right? So we say around VDD. And you can see as VDS is around VDD, which is far greater than Vx, that is my VGS minus VT. So my device is in saturation region, right? So it is very important to remember that whenever in a CMOS circuit, whenever the pull up network or pull down network, when it starts to get on, it starts from saturation region and not linear region. If you look at the curve of a MOSFET, what we expect the curve of a MOSFET? Something like this. At first it enters it when VGS is greater than VT, and this is my VDS and this is my ID, it starts in linear region and then enters saturation region. This is not the case for our MOSFET. I think sir has told it also using that graph where he has superimposed it like this, and he must have taken the mirror image, then he must have shifted it here, and you must have find some region of operation like this. Okay, if you carefully look into it, you will see in CMOS circuit the circuit starts from saturation region, then enters the linear region. Okay, so here in this region it would be my my PMOS would be in linear region still, and NMOS in cutoff region. NMOS in saturation region. Okay, D is similar to B. So here PMOS would be in saturation region and NMOS would be in linear region. I can go into details, but it's the logic is same. I have done it for PMOS, so you can do it easily for NMOS. And in E, my PMOS would go to cutoff region and my NMOS would go to linear region. Okay. Now there is an intermediate region here. Sir has not shown it. Let us consider it as region C. Okay. Guys, please, if you guys feel confused at any point, just tell me. I'll be more than happy to explain it to you. In region C, you can see the input voltage. This is also called the trip point or the threshold voltage of a transistor. Okay, this point. Let me call it Vm. Okay, generally it is taken a straight line which is equals to Vm, whose equation is V in equal to V out is taken, and wherever it cuts it, we call it the trip point of the transistor. Generally here this voltage is equals to VDD by 2, VDD by 2. X and Y axis are equal. Okay, so for region C, for NMOS, my VGS minus VT would be equals to, here you can see my gate voltage is also VDD by 2, my output is also VDD by 2. Okay, it is VDD by 2, source is 0 and minus VT, and my VDS would be equals to VDD by 2 minus 0 because source is 0. So you can see VGS minus VT, which is VDD by 2 minus something, is less than VDS because it is only VDD by 2, and in VGS minus VT there is a minus VT term here. Okay, due to this term my VGS minus VT is less than VDS. So my NMOS is in saturation region. Okay, now for PMOS, same thing. My VGS minus VT would be VDD by 2 V minus VDD minus VTP. Okay, so minus VDD by 2 minus VTP, and here VTP is negative, so plus of mod VTP, something like this, and VDS would be equals to drain, V drain is VDD by 2 and V source is VDD, so minus VDD by 2. Okay, so you can see mod of, therefore mod of VDS is greater than mod of VGS minus VT. So this PMOS is also in saturation region. So you can see in this region C, both my PMOS and NMOS are in saturation region. So basically when the input is low, my NMOS is in cutoff condition and PMOS is in linear condition. Then as I keep on increasing the voltage, as I keep on increasing this voltage, it enters a region where my NMOS starts at saturation region, where PMOS is still maintained at linear region. When I further increase this voltage at around VDD by 2, both my PMOS and NMOS goes to linear region. On further increasing, my PMOS from linear region, from saturation region, still in saturation region, but NMOS comes from saturation region to linear region, and when increased near VDD, my PMOS goes to cutoff while my NMOS stays in linear region. Okay, these are the region of operation for these 5 different regions. I just made it because what I feel that sir might give you this question at some different region, and in the exam he might ask you, if you guys are preparing for the exam, that what is the in which region of operation it is in. Okay, that's why I completely described it to you. Hope you have understood it. Okay, yes. Can you repeat again? Let me write it. What you were saying? What you were saying? Repeat again. Okay. Yes. Yes. See. Yes. See. What is happening here? Let us consider a PMOS. PMOS is little tricky to handle. Okay. There are a lot of conventions to deal with PMOS. The convention that I follow is, I keep the equation same as NMOS, only everything will be negative. VTP will be negative, lambda will be negative, that CLM, gamma, everything will be negative. Okay, there is something called a SPICE, level 1 SPICE model, all the parameters would be negative. That is what I consider. For your understanding, let me clarify it. Here, instead of VDS, we should, in cases of PMOS, if you want to work with PMOS, instead of VDS, we work with VSD. Okay, and instead of VGS, we work with VSG. If you take VSG and then take VT as negative, then you will get whatever I am saying, that you will get something as VSD. Sorry, yes, VSD would be greater than VSG minus VTP. Okay. So for simplification, because as I prefer working with VDS only, and I generally take VDS as negative, VGS as negative, so I have written mod of VDS is greater than VGS minus VT. Okay. See, okay, see, let me draw MOSFET here once again. This is my NMOS, lower one is NMOS, upper one is PMOS. Identify which one is drain, which one is source. Generally, this one is drain, this one is source, this one is gate, this one is gate, this one is source, this one is drain, right? Now in which direction current is flowing? For NMOS, current flows from drain to source, that is high potential to low potential, right? That's why it is used for discharging, the pull down network. And here the current is flowing from source to drain, right? So in NMOS we write the equation IDS equals to something, in PMOS we write ISD equal to something. Okay, this is the basic convention. You might like, if you study device level physics, even in circuit level physics, this is the basic thing, that we say IDS, and when you are saying for NMOS, for PMOS it is ISD, because current is flowing from source to drain, right? In PMOS current flows from source to drain, and in NMOS current flows from drain to source. And if you want further clarification, I can go why it goes from drain to source and all. Okay, you have to just look into, like, okay, fine. And this is the reason that like I have drawn it here also, right? I have drawn it here also. Now when sir has drawn you this curve, when he has drawn you this curve, right, he has drawn this curve in the lecture, right? So where does this curve comes from? You have to think on it. This is, let me give you an let me quickly go through it, okay, because I believe these kind of things are very crucial to understand the concepts. So this was my what? This was my VDS, right? This was my IDS. So for NMOS the curve would be something like this, right? But in case of PMOS, it is actually not VDS minus VSD. So I get in the left hand side, and it is not IDS, it is minus ISD. Okay, it is ISD equals to minus IDS. That's why for PMOS I get the curve something like this. Okay, so when I convert this ISD to IDS, I just take the mirror image of it. Okay, I just take mirror image across this axis and I get something like this. Okay, now here it is VDS, okay, and here it is minus VDS, this axis. Now if you remember, here in that case we take VSD instead of VDS, okay. And also generally in PMOS, if you see here, what we are doing for finding this VSD, we have to subtract, say V gate is here something, V input, and source is here minus VDD, source is VDD. So my VGS become V in minus VDD. So for such kind of operation we have to make a transfer in the right hand side by VDD. That's why it gets transferred and we get the circuit something like this. Okay, and these points of contacts are my operating points. Okay, if you draw much more, you will get this circuit as something like this, my load line. Okay, so this is the basic from where this circuit has been arrived. So directly tells you about this part in the first quadrant, but basically one is in first quadrant, one is fourth quadrant. It gets transferred in the, we take the mirror and then we move it by right hand side, then we get this curve. Okay, okay, fine. Now I know in which region of operation for the 5 cases, in which region of operation all my transistors are. So let's face the questions. The first question is region B. In region B we can see PMOS is in linear, NMOS is in saturation. Okay, so PMOS is in linear, NMOS is in saturation. This is the answer. And in region E, here it is asked about region E, right? Region E. In region E, you can see PMOS is in cutoff, NMOS is in linear. So PMOS is in cutoff, NMOS is in linear. Right? Clear? I hope it's clear and I'm not going too fast. Okay, the next question. Select the correct statements. Saturation current IDS is maximum when Vin equal to 5 volt. Okay, so as far as how much I have understood the question, they are talking about a technology where VDD equals to 5 volts. Okay, and they are saying what I've understood from the question, they say they have designed an CMOS based circuit, and they are saying what is the question? Okay, when my V input is equals to 5 volt, they are saying my V output would be my IDS is maximum. Saturation current IDS is maximum. Saturation current is an important term here. Okay, see, when my V in is equal to 5 volt, I am around this region of operation. Okay, here my NMOS is in linear region and PMOS is in cutoff region. So my device doesn't have any saturation current. So saturation current cannot be maximum here. So it is false. Okay, this is false. Understood? Hope it's clear, right? Okay. The next statement is, for an ideal inverter, ID NMOS equals to IDS PMOS when Vin equals to 2.5 volt. Okay, let's see. I'll be solving it, then I'll be making one statement for your understanding. See, my IDS NMOS, what will be my IDS NMOS? It would be mu Cox W by L VGS minus VT by 2, because it is in saturation region, right? So I've taken saturation current equation. And IDSP would be mu Cox okay. So as generally mu n is twice of mu p, so let me consider W by L of p is twice of W by L of n, so that I get a symmetric kind of structure, symmetric rise time and fall time. And here, as my V input is 2.5 volt, which is VDD by 2, my output would also be equals to 2.5 volt, because it is a symmetric structure. Okay, so it's simple. You can see here my VGS would be equals to, VGS is 2.5 minus, for NMOS minus 0, so it will be 2.5 minus VT. It would be something into 2.5 minus VT square by 2, and this would be this term into VG is 2.5 minus 5 minus VT by 2. Okay, VT by 2. So it will be minus 2.5 minus VTP, but VTP is negative, so I will get, if I take square, I will get the same term as 2.5 minus VT mod of VT by 2 whole square. So you can see basically my IDS N and IDS P would equate with each other. Okay, so this statement is true. This statement is true. This is true. Okay. And the third one is, for an ideal inverter, the static power dissipation is 0. Now here you can see, what is static power dissipation? The power that is dissipated when my inverter has made transition into one of the extreme cases. Okay, so let us see. So if this is the my inverter output, this is the V output and this is the V input, then you can see here, in this case my PMOS is on in linear region, PMOS is in linear region, but NMOS is in cutoff region, right? And in this position my PMOS goes to cutoff region while my NMOS stays in linear region. So when my PMOS is on, my NMOS is off. Similarly, when my PMOS is off, my NMOS is on. So in this circuit, at a given time, in these two extreme conditions, at a given time, there is no direct path from VDD to ground. There is no direct path. Okay, so there will be no power dissipation because there is no current flowing from VDD to ground. Okay, so static power dissipation is equals to 0. Now it is mentioned ideal case. In non-ideal cases, what happens? There is some leakage currents through this PMOS and through this NMOS, sub-threshold leakage current, right? So like this is the my IDS versus VDS curve. So when this region is, it goes to saturation region, we call it is on, but in this region also some small amount of current is still flowing in this region. So some small amount current might flow and lead to some small amount of power dissipation. This is called static power dissipation. But in ideal case, we will take it as 0, and that's why there will be no power dissipation in ideal case. So for an ideal inverter, the static power dissipation is 0, true. So the answer is false, true, true. This is the answer, false, true, true. Fine. Now, okay. Now let me talk about an interesting thing here. let me talk about an interesting thing. See, basically, you will be, I hope you will be studying about noise margin and all in the subsequent lectures. Okay. Basically, when you operate an inverter or any CMOS design, which consists of inverter or buffers and all, there is this region. See here. In this region, okay, let me go clean one. Okay. In this region, you can see NMOS is here off, PMOS is on. NMOS is off. Here NMOS is also on, PMOS is also on. So in this region, when there is some switching, some power will be dissipated here, because both NMOS and PMOS is on, and there will be a direct path between VDD and ground. Okay. This is called dynamic power, because during switching operation, when my input voltage is increasing, at some point, at some transition point, as there is both NMOS and PMOS are conducting, so there will be some direct path, and it will lead to dissipation in power. It is called dynamic power. Now you can see we define two regions here. We draw slopes here and say this is my V output and this is my V input, right? So I find the point where dV output by d in V input is equals to -1. Okay, so I'll get 2 points, 2 such points, one here and one here. Okay, in this region between these 2 points, both my transistors are in saturation region. Okay, and dV output by dV input, it is telling about what? It is telling about the gain of the system, right? What is the gain of my system? So inside this region, my gain is more than 1, right? So can you think what could be its application as its gain is more than 1? It can be used to design amplifiers. Okay, now till now it is not used, but some research is going on to use this region of operation, as gain is very higher, to design amplifiers and all. Okay, what is the, now we always ensure that when I give any output, say I am giving a logic low as input, my logic low should not cross this point, and my logic high should not cross this point. I can take VDD as output, I can take this one as output, but not here. I cannot take this one as output. Why? Because if I give such a point as my input, it will be in high gain region. Okay, and as here gain is high, if some noise arises, I will not get this one as output. If some noise arises, this noise will get amplified due to high gain, and it will either switch to VDD, or it will either switch to some higher value, or it will switch to some lower value, depending on the voltage of the noise. Okay, so we always avoid this region. We always ensure our circuit never goes to this region of operation while designing CMOS circuits or any other, most of the other logics. Okay, we avoid this region of operation. So this is an interesting thing that I wanted to talk with you guys. This is more of research or PG level, but I wanted to give you an insight about what is happening here, so I brought it up. Okay, so are all the guys with me till now? I hope it's not going over your head. Anytime you can just stop me and you can ask me anything. Okay, I will try my level best to make you understand. Okay, let's move forward. Okay. It has hardly been 45 minutes. I don't know how I will cover the rest 1 hour 15 minutes, because if I quick it will be over in 10 or 15 minutes. So I am trying to elaborate it as much as possible for your better understanding. Okay, select the correct statement. The skew ratio is defined as gamma equals to beta NMOS by beta PMOS. Those sir is directly given in class that the skew ratio as skew ratio gamma as beta PMOS by beta NMOS. Okay, so it is false. Now he has explained it in terms of beta, in terms of skew ratio gamma. But I will let me talk it like how I understood. You don't need to remember what is this skew ratio and how, if skew ratio is more than 1, whether PMOS will be strong or NMOS will be strong. Let us simply see the output characteristic of a CMOS inverter. See, it is say it is VDD, and say it is VDD by 2, it is 0. It is VDD. It is VDD by 2. It is in symmetric CMOS circuit. So circuit looks something like this. 2 means its W by L ratio is twice of NMOS. Okay. Now, what will happen if I increase the strength of this PMOS? What will happen if I increase the strength of this PMOS? Anyone? What will happen to this curve? See, as my PMOS strength is increased, my current through the PMOS is increasing. This current, this charging current is increasing. The current that charges this load capacitor connected at the output. Okay. So, it will try to take the output to it will try to, so when my input, say I am at this point VDD and I am reducing this voltage. Now, if my strength of the PMOS is increased, as my current is increasing, so my circuit will reach this value VDD at much earlier stage. So if I increase the strength of my PMOS, my curve would move to right hand side. Okay. Similarly, if I increase the strength of this NMOS, what it will do? It will try to discharge it much more quickly as compared to an standard CMOS circuit where PMOS W is twice of NMOS. Instead of that, it will try to discharge it to ground at more earlier time. So if I start from this point and if I keep on increasing my V input, sorry, I have written opposite. So if I try to increase my input, if my strength of NMOS is increased, what it will do? It will try to reduce the output voltage to ground to 0 volt at much earlier stage. Okay. So increasing the strength of PMOS shifts it to right hand side, and increasing the strength of the PMOS shifts the VTC, voltage transfer characteristic, to left hand side. And this very thing I have used in one of my recent works. So I was doing something where I needed a skewed circuit, not skewed, a circuit with asymmetric curve VTC I needed. At that time I have tweaked with this W by L values, and I have changed the strength of this PMOS and NMOS, and I got a circuit where I got the desired output characteristic that I was looking for. Okay, so these are some of the tricks that we use in circuit design. Okay, so the second point is a skew ratio greater than 1 signifies a stronger PMOS, and the DC transfer characteristic of the inverter shifts to right. So if PMOS is increased more than 1, if gamma is more than 1, that means PMOS is much more stronger, it will move to right hand side. So it's true. A skew ratio less than 1 signifies a stronger PMOS device, and the DC transfer characteristic of the inverter shifts to left. So it is saying gamma is less than 1. Therefore my beta PMOS is less compared to beta NMOS. So NMOS is much more stronger, so it will shift to left hand side, right? So it is but here it is saying PMOS is stronger. No, PMOS is weaker. Inverter shifts to left, it is correct, but PMOS is weaker than NMOS, so it is false. So the answer is false, true, false. False, true, false, right? Sorry, it is true. So sorry. Yes, it is false, true, false. Yes. Okay, see. See. So this is my load capacitance here, right? So say I have increased the strength, instead of 4 I have made it, instead of 1 I have made it 4. Okay, so my what will be my IDS, mu IDS, mu Cox W by L. Now W is 4 of W by L. Okay, VGS minus VT square by 2. Let me consider it in saturation region for simplicity. So what it is 4 times of IDS prime. IDS prime is my initial current, right? So my this capacitor will be discharging at a much faster rate compared to charging. It will be charging at rate of IDS, but it will be discharging at the rate of 4 IDS prime. Okay, it will be discharging at a much faster rate than it is charging. As it is discharging at a much faster rate, so when I will start to increase my voltage, my PMOS, my output load capacitance would discharge much quicker to the initial condition. Because why? Because in this region of operation, if you remember, in this region of operation, both my PMOS and NMOS were in saturation condition, or both were in on condition. Let me say, might be saturation, might be linear. But as my NMOS is much more stronger now, that's why the NMOS current would discharge this capacitor. PMOS is trying to charge it, but the discharging rate is much more higher, right? So my V output would start falling at much higher rate. Instead of falling in the original rate, it will start falling to ground at much higher rate. That's why it will shift to left hand side. Do you got my point? Do you get my point? Okay, okay, nice. Okay, fine. Let me move to the next question. Question number 6. Select the correct statements. When the input voltage to an ideal CMOS inverter is equal to the inverter threshold voltage. By inverter threshold voltage, he is meaning the trip point, the VM that I talked about. Okay. Okay. So it is given. My V input. Let me draw the circuit once again. It is given. My V input is equals to inverter threshold voltage. That is generally for a symmetric inverter, it is VDD by 2. Right? When the input voltage to an ideal CMOS inverter is equal to the inverter threshold voltage, both PMOS and NMOS devices are in linear mode of operation. So let's get back to what we discussed here. It is, we remember, when it is equals to this V inverter threshold voltage or trip point, both my PMOS and NMOS are in saturation region. I gave a detailed explanation why it is so. So it will now be useful. So they are saying at this trip point or this inverter threshold voltage, PMOS and NMOS devices are in linear mode of operation. So false, because they are in saturation mode of operation. Second statement, when the input voltage to an ideal CMOS inverter is equal to the input threshold voltage, both the PMOS and NMOS devices are in saturation mode of operation. True. We have already seen it. Why? Right? Sorry. Okay. So statement number 3. For statement number 3, if beta NMOS equals to beta PMOS, the inverter threshold voltage is VDD by 2. Okay. So for a long channel inverter made of long channel MOSFETs, the trip point voltage can be given by this equation: VTN plus root under gamma, we call it by gamma or R, VDD plus VTP. I hope sir has given this formula to you, divided by 1 plus gamma. Now what is the value of gamma? The value of gamma can be defined as, for long channel inverters, gamma is equals to let me write it as minus Kp prime Wp by Kn prime Wn. So Kp prime, Kn prime you might not be familiar with. So the term is something as Kp is basically mu Cox. Okay. So it is kind of, you can say beta p by beta n. It is kind of beta p by beta n, because LL will cancel, because L are generally kept same. And here Kp prime was considered to be negative, but in your convention Kp prime, beta p and beta p n might be both positive. Okay. So let me remove this negativity, it will be better. So and also as beta n and beta p are equal, my gamma would be equals to 1. Okay. So my Vm would be equals to Vtn plus root under 1 Vdd plus Vtp. Now for symmetric devices, symmetric technology, we can consider Vtp and Vtn are equal in magnitude. If my NMOS starts at if when VGS crosses 0.3 volt, if my NMOS starts after that point, similarly when my VSG would cross 0.3 volt or my VGS would cross minus 0.3 volt, my PMOS will also start. Okay, so I can take this Vtp as minus of Vtn divided by 1 plus gamma. Gamma is 1. So it would be, you can see Vtn will cancel, so it will become Vdd divided by 2. So for beta NMOS equals to beta PMOS, the inverter threshold voltage is Vdd by 2. Vdd by 2. True. So answer is false, true, true. Okay. Is it clear? Let me move forward. Same in the next question also. They have asked us to estimate the inverter threshold voltage for 65 nanometer technology node. Vt NMOS is 0.3 volt, Vt PMOS is minus 0.3 volt. As I just said right now, that I can take the mod to be equal, only Vt NMOS would be positive, Vt PMOS would be negative. That is what I did here. That is what I did here. Okay. So they have asked me to calculate the inverter threshold voltage, the trip point Vm. So I will be again using this formula Vtn. It's question number 7, right? To be Vtn plus root under gamma Vdd plus Vtp divided by 1 plus root under gamma. So basically I think sir will be giving you this gamma values and all, but you can use the gamma value that I have provided also to calculate the same if it is not provided. Only mu C of is W by L is given. So Vtn is 0.3 plus gamma is 4, so root under 4, Vdd is 5 volt and Vtp is minus 0.3 divided by 1 plus root under gamma, gamma is 4. So you will get 0.3 plus 2 into 4.7 divided by 1 plus 2, 3. So it will come 0.3 plus 9.4 by 3. So 9.7 by 3. How much it is? It would come 3.23 volt. 3.23 volt. Correct? This is how you can calculate the threshold voltage of a long channel CMOS based inverter. Okay. Any confusion? You can ask me. Even I am feeling tired. Okay, fine. Next question. Same. Estimate the inverter threshold voltage for the short channel current mode assuming operation in velocity saturated region. But the condition is given VCN is much less than VGS minus VT for 65 nanometer technology node. Okay. Here for velocity saturated MOSFETs with this condition, satisfying this condition, the inverter trip point equation narrows down to gamma VDD, if I can remember it correctly, it is VDD plus VTP plus VTN divided by 1 plus gamma. Now you might ask me the question, none of you guys have asked where this equation is coming from. Any answer? You must be curious, right? Where I am getting this equation for different conditions. For long channel device I am getting one condition, one equation. From short channel device I am getting one condition. Where I am getting it from? So basically nothing you have to do, it's very simple. See, if this is my curve at this point of operation, what happens? My IDSP and IDSN becomes equal to each other, right? So if I simply write this IDSP in saturation with IDSN of saturation, and if I take the input as Vm and output as Vm, so input is Vm means my Vg is Vm, my output is Vm means my V drain is Vm. Just write this equation and just solve it. For long channel devices you will get that equation, this equation, you will get this equation, sorry, you will get this equation. And for short channel devices, velocity saturated devices, you will not get this equation. This equation comes up after a special condition. But what equation you will be getting is, you will be getting this equation. Let me write it for you so that you know what is happening. You will be getting the equation of Vm something as Vm equals to Vdn plus Vd saturation of n divided by 2 plus gamma Vdd plus Vtp plus Vd sat of p divided by 2 whole divided by, this is one big bracket, 1 plus gamma. Okay, if you know the value of this velocity saturation, the VDS, the voltage as VDS voltage at which the velocity saturates, you can easily calculate the inverter trip point. And then they have taken some assumptions and they have reduced this expression to this expression. Okay, so my Vm would come to, gamma is given 3, so 1 plus 3, and here 3, Vdd is 5, Vtp is minus 0.3, Vtn is 0.3, so it will come 3 into 4.7 plus 0.3 divided by 4. So how much it will come? It will come something as 14.1 plus 0.3 divided by 4. 14.4 divided by 4 is 3.6 volt. I will be getting this voltage 3.6 volt. Clear? Okay. Okay, let me okay, before going forward, let me just give you another interesting idea to think upon. See, here sir has written it, if you remember, that my IDSN and IDSP becomes equal at this inverter trip point, right? But the thing is, when I bias my inverter in any condition, say be it region A, region B, C, D, E, anything, at first my PMOS is in at first my PMOS might be in linear or cutoff, anything. Sorry, let me phrase it in this way. Let me talk about the current. My IDSP is always equals to my IDS of n. This is what basically I am trying to say. This is basically what I am trying to make the point. Now we will say why. See, in an inverter, say let me take this inverter. Let me draw an inverter at some free space. Say this is an inverter, okay? And I have applied some input voltage here. Say I have applied VDD. So initially only my NMOS will be turned on, and if there is any voltage stored here, it will get discharged. Okay, it will get discharged. It will get discharged. Once it gets discharged, this voltage will become 0, right? When this voltage becomes 0, my VD has become 0, drain voltage has become 0, and source voltage is also 0. So what will be my current? My current will also become 0. And here the current was already 0, right? The charging current was already 0. So at equilibrium, you can think both, my inverter is trying to bring both the currents for a matched inverter where PMOS is W is twice of NMOS. It is trying to equate the currents at all time. Okay, so this output voltage would change accordingly, so that I get equal currents, charging and discharging current. When I bias it, of course when I apply VDD, it will start discharging, and my IDS N would be much higher than IDS P. But at equilibrium, it will try to discharge the whole voltage stored here, and for me to get a current which is in the NMOS and PMOS current is equal to 0. Similarly, if it was 0, this would have charged this one to VDD, and again my VDS would have become VDD minus VDD. So it would have become 0. Again my current would have become 0. Okay. So at equilibrium, like you should think on this point, right? You can do some study also in this point, about this point, and go into details. That I just give you the brief overview of what is happening, but you can study in detail what is happening here. You can see that, you can check the equations and all, because your VDS becomes 0, so your current should become 0, right? Okay, and they are in linear region, not in saturation region, that it will be independent of VDD. So you can think on it. Okay, so next part is select the correct statements. Okay, NMOS pass transistor charges till VDD passes degraded logic 1. Now I hope you guys have studied about pass transistor logic. I'll be talking about it. Okay. Question number 9. Fine. So I have an NMOS. Okay. This is drain, this is source. This is VDD. Here is my load capacitance, CL. And remember, what I am saying is load capacitance always, this might not be a physical capacitance, okay? This might be the gate capacitance or the drain capacitance of the next stage CMOS circuit. This CL does not need to be a physical capacitance. This might be the parasitic capacitances of next stage CMOS circuits, okay? Okay. Okay, let us look. Say I am applying such a pulse where input was initially 0, then it became VDD. This is not important for you, but this right hand side, this one I just showed you to, so that you can think on it. Okay. Okay. So here, remember, the problem only arises in pass transistor logic when my source gets charged with time. Why? Because in my current expression, you will remember there is one VGS term and one VDS term. Okay. So if my source is getting charged with time, my VGS would come down, because either I am giving voltage both at gate and both at drain. So say my VG is 5 volt, VG is 5 volt and VD is also 5 volt, and my source has started getting charged. Source was initially 0, but it also become 5 volt. So my VGS and VDS both will become 0 volt, right? So my current will become 0. So we always will try to ensure that my source terminal is not getting charged. Fine. So here you can see I have given a pulse which was initially 0, later I made it VDD. Now see what happens. The condition that I should remember is my VGS minus VT should be always greater than equals to 0. That is, my VGS should be greater than threshold voltage. That's it, nothing else. So here VG minus VS minus VT should be greater than threshold voltage. Okay. If I take VS to right hand side, it becomes VG minus VT should be greater than VS. And what does this equation telling me? This equation is telling me that the VS should always be less than this expression. So VS max cannot, the VX max should be VDD minus VT. That is VG minus VT, and in VG what I am giving? VDD. So whatever I do, my source voltage will not get charged beyond VDD minus VT, this volt. This is the maximum volt that I can get is at this point Vs. Okay, this is the maximum volt that I can get at Vx. So NMOS pass transistor charges till Vd passes degraded logic 1. So whether it is true or false, NMOS does not charges to till Vd, it charges up to VDD minus Vt, so it is false. Okay, so it is false. Now the next statement, NMOS pass transistor discharges to 0, passes logic 0 successfully. Now let us look into that. This is again an NMOS pass transistor. Okay, now what I am saying, it discharges to 0. Okay, so now I should draw it like this. Now here VDD is connected. I am again giving such kind of pulse in the gate. Okay, and it is connected to ground. Let me consider here an capacitor is present, the CL, which was initially charged to VDD. Fine. Okay, now let us see which one is drain, which one is source. Can anyone tell me? Drain will be which one, source will be which one? This will be my gate, this will be my source, this will be my drain, because in MOSFET drain is always considered the terminal which is at higher potential. As here this terminal is in VDD and this terminal is in ground, so it is considered as source and this is considered as drain. Fine. Similarly here also it should be VGS minus VT should be greater than equals to 0. So VG is VDD minus Vs. Vs is here 0. So VDD minus Vs minus VT should be greater than equals to 0, and Vs here is 0. So simply VDD is greater than equals to Vt. Therefore, Vs. Just give me a minute. Yes, Vs is here 0. So my source can reach up to 0 volt. Okay, I should rephrase my equation. How to rephrase it? Just give me a moment. VDD minus VT. See, what is happening here, I should not write it like this. What is happening here, as my load capacitance is discharging from drain to source, as there is no load capacitance present here, okay, so my source voltage would not go up. Okay, my load voltage, my source voltage would not go up, unlike the condition when my CL was connected at source. Okay, as it is connected at drain right now, my source voltage would not go up. So my source voltage, as it is 0, so I can write my Vg minus Vs minus Vt greater than equals to 0. So as my source voltage would not go up, I can assume the source voltage can go up to 0. Okay, so let me write it like this. As my source voltage can go up to 0 volt, so my CL would be able to discharge completely from VDD to ground. Okay, so the voltage that I have provided here, this 0 volt, will be passed on to this CL. My CL will also become from VDD to 0 volt. Got it? Forget about this expression. Okay, so that's why this is the exact reason that at pull down network we use NMOS circuits, and at pull down networks in CMOS, and in pull up networks we use PMOS circuits. Why? PMOS can pull up to logic, it can pull up to VDD, but it cannot pull down up to ground. It will be able to pull down up to only mod of VTP. Okay, but my NMOS circuit can pull down up to ground, but it cannot pull up to VDD. It can only pull up to VDD minus VTN. Okay, that's why for pull down networks we use NMOS, and for pull up networks we use PMOS. Okay, so the next statement is NMOS pass transistor discharges to 0, passes logic 0 successfully. This is true. Okay, that's why they are also called strong 0 or weak 1. Okay, NMOSs are called strong 0 or weak 1 because they can pass 0 successfully, but they cannot pass VDD completely. They will only be able to pass VDD minus VT, so it is called weak 1. Okay, let's move forward. Okay, same PMOS pass transistor charges till VDD, passes logic 1 successfully. Yes, PMOS in the same logic that I have shown you, we can say that PMOS transistor can pass VDD successfully. It is nothing. You just have to draw a PMOS transistor. Okay, and similarly connect a load capacitor here. Identify which one is drain, which one is source. Assume a voltage VDD at the ground, and then check whether it is able to discharge it completely or not. You will see a PMOS, you will not be able to discharge it completely. It will be only be able to discharge it up to mod of VTP. VTP is negative, so I am saying mod of VTP. But a PMOS transistor will be able to charge it if this was VDD and this was the output load capacitance here. Sorry, the reverse. It would be able to charge it completely up to VDD. That's why PMOS circuits are also called strong 1 or weak 0. Okay, so PMOS passes charges till VDD, passes logic 1 successfully. It is also true. PMOS passes PMOS pass transistor discharges to 0, passes degraded logic 0. It is true that it passes degraded logic 0, but it doesn't discharge to 0, discharges to mod of VTP. So it is false. So the answer is only 2 and 3 are correct. Only 2 and 3 are correct. Got it? Hope it is not it is not turned into a boring lecture, because I am trying to give you interesting facts in the middle so that it doesn't get boring. Okay, fine. The last question. Select the correct statement. Okay, so here they are talking about transmission gate logic. So should I talk about transmission gate logic before talking it or after it? Okay, let me just go through this question, then I will be talking about transmission gate logic a little bit. Okay, so the first point is, in a transmission gate for a rising input, PMOS conducts from 0 to VDD, whereas NMOS conducts only from 0 to VDD minus VT. Let us draw a transmission gate logic, then we will understand what is happening. Transmission gate logic is nothing but a NMOS and PMOS connected, end-to-end connected in kind of parallel fashion. Why such kind of switches are used? Why transmission gate is used? One reason, as I know that NMOS can only pass a strong 0 but cannot passes a weak 1 or passes a degraded VDD. Well, PMOS can pass a strong VDD but passes degraded 0 or weak 0. That's why what we do, we connect them in parallel. As a result, as they are in parallel connection, my resistance will also be low, but the main benefit that we get is it will be able to pass any voltage. Okay, this transmission gate will be able to pass any voltage that we require. Okay, so the first one is uh, PMOS conducts from 0 to VDD. As PMOS is strong one, so it is true that PMOS conducts from 0 to VDD, whereas NMOS conducts from 0 to VDD minus VT. It is also true. NMOS is weak one, so it will only be able to pass up to VDD minus VT. So it is first one is true. Second one, in a transmission gate for a rising input, right? For a rising input. PMOS conducts only from 0 to VDD minus T. No, it's false. It can conduct from 0 to whole up to VDD, whereas NMOS conducts from 0 to VD. It is also false. As input is high, so it will only be able to conduct up to VDD minus VT. So this one is false. Okay. Third point, in a transmission gate for a falling input, now they are saying it is a falling input. In a transmission gate for a falling input, PMOS conducts from VDD to 0. Now PMOS is what? Strong one or weak one? PMOS is strong 0 or weak 0? PMOS is weak 0. So it is false. It will only be able to conduct from VDD to mod of VTP. Okay. Whereas NMOS conducts only from VDD to VT. No. NMOS is strong one, so it will be able to conduct from VDD to 0 volt. So it is also false. Final one will be right. Final one is, in a transmission gate for a falling input, PMOS conducts from VDD to VT. It is true. Whereas NMOS conducts from VDD to 0. It is also true. So only 1 and 4 are correct. Fine. Only 1 and 4 are correct. Now as we have almost 35 minutes left, more than 35 minutes left, I will be talking quickly about some interesting points. Okay. First of all, let's start with transmission gate. Okay. So basically this is our transmission gate. Okay. This is input A, this is my output, and these are my select lines as S bar. Okay, fine. Now as I already mentioned, this gate is able to pass any logic, any input logic without degradation. But this transmission gate has one important application. I would like to talk to you about it. Can anyone tell me where this transmission gate can be used, reliably used? Okay, no one, because you might not know, because you might not have read about it. Fine. So we know about multiplexers, right? What is a multiplexer? This is the structure of a multiplexer. Say I am drawing a 2:1 multiplexer. Okay. So there is A, B, and there is one input, control signal S. There is output. So output is basically S bar A plus SB. Okay. Now if I want to design this circuit using CMOS gates, CMOS logic, how many gates I will be requiring? Anyone? Let me consider S and S bar both are present. I don't need an inverter to get S bar. How many logic gates will be required to get this output S bar A plus SB? Anyone? Don't get shy. Anyone can just unmute yourself and just tell me. It's not that difficult. Okay, just let me tell. See, there is one OR gate. So one OR gate is required. Here, as for SB, one AND gate will be required, and here for S bar A, one AND gate will be required. So total 3 gates will be required. One 2 input or 1 2 and 2 input AND. Now, if you go and see the CMOS circuit design, for designing these circuits, I need at least 4 transistors. Similarly, here I need 4 transistors, here I need 4 transistors. So total I need 12 transistors to design this logic. Now what if I could have designed this circuit with much lesser transistors, but with same rail to rail swings and same advantages of a CMOS circuit. In this part, in this kind of conditions, the real use of this transmission logic gate comes into picture. What I can do, I can simply make this circuit. Can you explain what happens when PMOS and NMOS are interchanged in CMOS inverter? Sure, I'll be covering that. See, but let me go through this one first, okay? Say this is Y1, this is Y2, this is output Y. Y is equals to Y1. It is called wire or operation, wire or Y2. Okay, and this implements the logic S bar A plus SB. Check with S bar and SB, you will get this logic. So I can, here only I require 1, 2, 3 and 4, only 4 transistors I am requiring. So much lesser number of transistors I am requiring here. Okay, so instead of 12T, I only need 4 transistors to design a 2:1 multiplexer. Similarly, I can design a 64:1 mux. You can think how many circuits, how many transistors will be required if I use CMOS logic. But here, how many I will require? For 64:1, it will be simple. Say say I0, I1 up to dot 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 up to 63, right? I63, 1 NMOS, 1 PMOS. And what will be the control signal? It will be, say, something as D0 bar, D1 bar, dot 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 D63 bar. Okay, and in muxes we only have 5 control signals, right? For 64, how many control signals? I will have control signal 6. So I will be using a decoder. Dot dot dot. It would be say S0, S1 to S5. Total 6 control signals, and I will be getting output 64 outputs. This D0, D1 dot 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 D63. So you can see, using much lesser number of transistors, I can make much complex muxes if I use this transmission gate logic. So this is one of the most important use of this transmission gate logic. Okay, Swati is asking, can you please explain what happens when PMOS and NMOS are interchanged in CMOS inverter? Sure, I can explain. Hope this question is not part of your assignment. Let me explain what happens. So basically what you are saying is this circuit. Okay, this is VDD, this is ground. Okay, so now let's see what happens. So this is my V input, this is my V output. Say my V input is less, the V input is small. Okay, V input, let me divide it VTN, VDD by 2 minus VTP, so mod of VTP, VDD. Okay, let's see what happens. So when my V input is less than VTN, it is off, this is on. Okay, but will it be able to reach VDD? No, because in pass transistor logic, if you remember, my PMOS can only pass a weak 0. So it will not be able to, this is by the input of that pass transistor logic that I talked before. So it will not be able to pass ground here. Okay, what it will pass? It will pass something as when it is very small, it will pass something as output should be something as VTP. Output should be something as VTP. Okay, and when my V in is VDD, my NMOS will turn on, but will it be able to pass VDD? No, it will only be able to pass VDD minus VTN, because NMOS is a weak one or strong 0. Okay, so instead of VDD in this region, it would be VDD minus VTN. So we will be getting such kind of circuit. Okay, we will be getting an output which resembles a buffer. The only difference is, instead of enhancing, the output is getting much more distorted. Instead of getting rail to rail swing from 0 to VDD, what I am getting is a swing of VTP to VDD minus VTN. Got it? So this will be my output. It will not be an, first of all, it will not be an inverter. It will act as a buffer, and its output will be like the swing would be much more degraded, and we will not get a rail to rail swing. Does that answer your question, Swati? Okay, okay, nice. Any more question? We have more half an hour left. If not, let me talk about a question that previous day one of you have asked. I have explained on that day what it is, but let me rewrite it. One day, previous day, one student has asked me that what she has seen some expression where V mean was used. So I said it is nothing. They are just incorporating all the 3 equations of current of a MOSFET into a single equation. This equation is called unified current model, and the equation for NMOS in unified current model is mu n Cox W by L V mean VGS minus VT minus V mean by 2 into 1 plus lambda VDS. Now let us look into all the terms. First of all, this term comes due to channel length modulation. This is the CLM coefficient. It is an empirical model parameter, and it is called channel length modulation coefficient, lambda. Okay, this is not H, this is 1 plus. This is 1 plus. Okay. Second, this term you have learned it as beta n, and this is the aspect ratio. Right? Now, what is this V mean? V mean is nothing but minimum of VGS minus VT, comma VDS, comma VD set. What does this mean? This means if my VGS minus VT is least among these 3, then I will be replacing this V mean with VGS minus VTN. If VDS is least in these 3 terms, then I will be replacing this V means as VDS. And if VD saturation, if it is a short channel saturated device, and if VD set is less than both VGS minus VT and VDS, I will be replacing this V mean with VD set. Okay, it's simple. It is basically for what it is for. It is for saturation. It is basically for linear. It is basically for velocity saturated devices. So for saturation, I will get the equation as mu n Cox W by L. I will be replacing V mean with VGS minus VT, so it will become VGS minus VT square minus VGS minus VT square by 2. So it will become mu n Cox W by L VGS minus VT square divided by 2. The equation that we got in the previous class, if you remember. And I told you that unified current model, the expression, this equation is not that important if you know all the conditions and all the biases. So basically it is an approach to incorporate all the conditions in a single expression. Similarly for linear it will become for this is for saturation. For linear it will become mu Cox W by L, and mean will be replaced by this VDS into VGS minus VT minus VDS by 2, right? Simple. For velocity saturated, my handwriting is not that good, sorry for that. IDS velocity saturated, it will become mu Cox W by L, VDS saturated, VGS minus VT minus VDS saturate by 2. So these are the three equations that we use. It has incorporated all these three equations in this equation of current. And remember, there is something called as a level 1 spice model. What is level 1 spice model? See, when you simulate a circuit, be it analog or digital, we use compact models or models for them. Okay, like you must have heard about GPDK 180 nanometer technology, or ASAP 7 nanometer technology, or TSMC 45 nanometer technology. These are the different foundries that fabricates ICs, and they have their models for them. Okay, so for designing circuits, we need to know about the word WL. See, W and L is on our control, but we need to know about the current and what will be the expression of current, and if I use what VG, VT, what IDS I will get. If you use some simulator like HSpice or Spectre or Virtuoso, that is cadence, or even a simple simulator like LT-Spice, you will be using some models, and this model contains all the rules for designing VLSI circuits. Okay, so there are basically 5 level 1 parameters, and these 5 parameters are Kn prime, Vd set, lambda, Vth0, and gamma. Gamma is not that skew factor here. Gamma is body parameter, body effect coefficient. Okay, Vth0 is the threshold voltage. There is some expression of Vth as Vth0 plus gamma root under Vsb plus psi s minus root under psi s. So every time you run a simulation, basically in the behind, your circuit is solving all these equations continuously and giving you the results of the outputs. The outputs that you get at the end of the circuit analysis is being obtained by solving thousands of iterations of such numericals. Lambda is CLM parameter, channel length modulation parameter. Vd set is this velocity saturation voltage, and Kn prime is nothing but mu Cox W by, no, not W by L, only mu Cox. Kn is mu Cox W by L, Kn prime is mu Cox. These are the 5 parameters that were included in level 1 spice model. Nowadays, the models that we use, it contains thousands of such parameters. Okay, thousands of such parameters. For mobility, you will be getting 15-20 parameters just for mobility mu. For CLM, you will be getting 15-20 parameters, and so on. And more parameters you include, more accurate your circuit becomes, but the runtime increases with number of parameters that you are using. So you have to learn a trade of that, how many parameters generally we use. If you go to lower technology nodes, more variations come, more physics, quantum tunneling might come, gate induced drain lowering leakage might come. So we have to include more and more parameters to make the results more accurate. Okay, and there are lots of interesting phenomena that happen in MOSFET. Like we were saying that mobility of NMOS is twice the mobility of PMOS. But interestingly, when you go to low enough nodes like 7 nanometer or even 15 nanometer or so, 24 nanometer, what happens? Something called as stress effects come into picture, and this mobility of NMOS and PMOS almost becomes equal. So you don't need to maintain this twice WP for WP equals to twice of WN, that you don't need to maintain. So there are many interesting phenomena that happen in VLSI circuit, and as we are shrinking down our technologies, new problems comes, and to solve these problems we are finding the physical reason behind them, the physical reason, or we are trying to come up with empirical models to solve them. We are trying to explain them, and we are trying to curve them, or we are trying to solve these problems. So this device and VLSI circuits is really an interesting domain to work on. Okay, so if you guys are interested and if you do your higher studies in this domain is really an evergreen domain with lots of interesting topics, research topics to work upon. Okay, so I think you guys have also studied about skewed gates, so let me quickly talk about skewed gates for a minute or two. See, generally for an inverter, this is our inverter, right? This is our inverter. Now this is an if WP is twice of WN, the current, charging current and discharging current, the charging current and the discharging current are equal. So I get equal rise time and fall time. Okay, but there might be situations when I don't require an equal rise time and fall time. Got my point? There might be situations, there might be applications where equal rise time and fall time is not required. Like I work in memory, okay, I design memories. So in memory domain, we don't require equal rise time and fall time. If you have studied SRAMs and all, you will remember that uh, when one of the input, like say I generally prefer one of them, say either the discharging or the charging, there is something called as bit line and source line in SRAMs, okay, SRAMs or flash memories and other technologies. So I generally want the bit line to move from 0 to 1 at much quicker rate than moving from high to low, 1 to 0. Okay, so what I need a fast charging path compared to and I can afford a slower discharging path. Now to achieve to make one path faster than the other, some techniques are being used. One of them is skewed gates. What I do, I intentionally make one of the transistor weak. So you have not studied it, but there is something called as logical effort G. Okay, there is something called as logical effort or G. It is basically the ratio of all these capacitances that you see here by capacitance of unit inverter, that is this inverter, where NMOS is 1 and PMOS is twice, W of PMOS is twice of NMOS. So generally we try to reduce this logical effort for the for one of the inputs, and that's why we use unbalanced, unmatched gates. We also call it skewed gates. So say this is basically an circuit with same rise time and same fall time. Okay, but what I can do, I can either make it a low skewed circuit, when I make it a low skewed circuit, instead of 2 I will be using say lesser values, say 1 or 0.5 if it is allowed. All the times 0.5 is not allowed, in some technologies it is allowed. So what will happen, my discharging current is much more higher than my charging current. Okay, my discharging current is much more higher than my charging current. So my the fall time would be much more lower than my rise time. Okay, this is called a low skewed circuit. Okay, here my rising time is increased but my falling time is reduced. Okay, so it will if I need circuits where I need quickly to discharge a word line or bit line, I'll be using this circuit. Where and if I want a situation for an application where I need quickly to charge my word line or bit line, I'll be using high skewed circuit. This is an PMOS. This one, say I'll be keeping it at 2, but instead of 1, if it is allowed, I'll be making it half. So here my rise time will be reduced, but my fall time would increase. Okay, Basically because here my charging current has become much more higher compared to my discharging current. Okay, so one of the delays will go up and one will go down depending upon my application. I can design skewed gates as per required. Okay, so skewed gate was there I think in your discussion topic, that's why I thought of including it. Okay, fine. Any questions? If you guys don't have any question, then I'll explain one more small topic, and if you guys have any question, then I'll be discussing the question only. So please, anyone, if you want, you can unmute yourself and you can ask questions to me. Any question? I hope it is not boring, right? I'm trying to not make it boring. I'm trying my best, but I don't know if it's still boring. Then I don't know. You guys can even ask questions, or if any regarding to microelectronics and VLS or VLSI. If any other question is there, I will still try to solve it. If you want to know something, higher studies or something, or in which areas research is being held, I can try to uh, try to make some comments about that also. Uh, so anything you can ask me related to these topics. Yes, Netra. Sure, sure, sure. Yes. No, no. You misunderstood me. Okay. See, noise will not be high, noise will be same. Generally, when you design circuits, there is always inherently some noises present in the circuit, right? Sure. So some such kind of noises are present in the circuit. Okay. Short noises, salt and pepper noises and all. So depending upon the circuit, noises are present. But in this region, as my gain is more than 1, my noise will also get amplified. That is what I am saying. Got my point? As my gain is more than 1, my input will of course be multiplied with the gain, so as the noise. That's why I'll get a very high noise at this range. In this range, I'll get a very high noise. And this noise might, or generally what it will do, it will either switch. See, I have biased my circuit in this point. I have given VDD by 2. But at output, I will not get VDD by 2 after a few time, because due to noise, as noise is high here, it will either switch to at such a point, or it will switch to such a point. Sure, but see, how to make you understand. See, my signal will also get amplified, okay? But what is the range of inputs? 0 to VDD, okay? So I was giving VDD by 2 as input. I was giving VDD by 2 as inputs in digital, okay, to bias it here. Now, if you remember analog topics, what do? We generally look at small signal gains, right? We bias at a particular point where gain is high, and at that point we try to make a small signal input, and that small signal input gets amplified to a large signal, right? If you remember that. Here VDD by 2, my input is a bias point, and any signal, the noise that will come will act as a small signal, and it will get amplified, and it will switch my output to some other values, okay? And if I use such a circuit, like this is the symbol for an inverter, right? If I use two back-to-back inverters connected in feedback, I get some curve, something like this. This is called a butterfly curve. I get something like this, okay? So what happens if it is VDD by 2? Generally, due to noise, in this kind of circuit, this is much more prominent. It generally will switch to either ground or VDD. Here the switching will not be to ground or VDD, but to some intermediate value. But if I use feedback connected inverters, end-to-end feedback connected inverters, I'll due to this butterfly curve, it will go to either VDD or to ground. Okay. And I hope you are the one who asked in the previous class about this unified current model. I hope it is clear to you. Okay, sir. Okay, sure. Other might have asked. Okay, any more question? Anyone else? I can see 11 people except me, 11 or 10 people. Any more question? Okay, fine. No more. Then let me discuss about one more topic quickly. See, for short channel devices, we are discussing about we are discussing about many short channel effects like channel length modulation, then velocity saturation. If you go into the device physics of it, channel length modulation is okay, but velocity saturation, it's not that easy. You have to understand about phonons and all, why it is getting saturated. If you ask this fundamental question, why it is getting saturated, you have to study about the device physics. You have to study about phonons and all, how they interact with each other and why it got saturated. Today let me talk about another effect which is called as hot carrier effect. It is more of a for device point of view, but let me talk about it. See, in the previous class we have seen, if you remember, this was my MOSFET structure, right? So basically it's this channel is basically an p-n plus channel, right? This is an p-n plus junction, not channel, p-n plus junction, this junction. Okay, now if you remember, I said that if it is my drain, if it is my gate semiconductor, and it is my source, this junction is reverse biased. If you remember, it is what I explained in the previous class. And in p-n plus junctions, if it is in reverse bias, in which direction my space charge region would be extended more? Can anyone tell me? It is basically p-n plus junction, right? You might have studied about p-n diodes. So if it is a p-n plus diode, then at which direction my space charge region would be extended more? Sure, P. So basically here I'll be having some kind of space charge region or space charge region here. Okay, so if you remember that avalanche breakdown or Zener breakdown, when electric field becomes very high, now when it is in reverse bias, the electric field generally becomes very high. Okay, so the electric field in this region is very high. It is lateral electric field, and there is also this drain voltage VDD, VD given here, So due to this voltage, there is a lateral electric field also, and there is electric field of the space charge region as well. So if you remember, I said the charge profile becomes something like this. Okay, when the VDS is increased much more than when VDS is increased more than VGS. So and also I apply a gate voltage here, okay, to invert this channel. So I am having an lateral electric field and I am having a vertical electric field. Actually, vertical electric field is in this direction, so electrons are getting attracted in this direction, towards the gate, towards this direction. So what happens in this region of operation? What happens sometimes? The electrons of the carriers gain so much velocity. They gain so much velocity due to this space charge region electric field. We start calling them hot. Why hot? Because their velocity increases, and if velocity is increased, their kinetic energy is half mv square. So my kinetic energy will also increase, and energy can also be written in the terms of kT. So if kinetic energy is more, my K is Boltzmann constant, which is constant. Boltzmann constant is constant. So my temperature, like the thermodynamics temperature of these electrons can be thought of as increasing, right? So that's why they are termed as hot carriers. So the electrons in this position gain so much of kinetic energy, and there is also this vertical electric field. What they do, they sometimes cross this oxide barrier. There is if you see the metal oxide semiconductor band structure, there is a big barrier in the middle. Okay, this is the oxide barrier, this is the conduction level, this is the valence level. So there is a big barrier in this T oxide region. So what can happen, this electron might get sufficient energy in this semiconductor. It is a p type, right? So p type. So the electrons uh, or if it was an n type, then holes. Okay, let me consider p type only. The holes here, the electrons that are coming here in this channel might get enough energy, and this electron might jump into my TOX. This electron might get lodged into TOX, causing not permanent, causing damage to my oxide. And if you have studied device level physics, you know in MOSFET, when there are charges present, the threshold voltage of the device shifts depending on the charge in the right hand side or in the left hand side. So these electrons can shift the threshold voltage to a new value, Vt plus something, say Vt del Vt something. So the threshold voltage of your device will change. So the current that you get for a particular VGS and VDS will change. So your device will start giving degraded performance to you. Okay, and this is called as hot carrier effect. Now how to solve this hot carrier effect? As you can see, the main problem, the main culprit is this region, right? This region, because here the electric field is very high and electrons generally get very high velocity in this region. So what we do in this region, we in this region, what we do, we add a small doping here, which is not n plus, which is a kind of n minus. It is called lightly doped drain, LDD. We do an LDD doping here. It is called an LDD. LDD is lightly or low doped drain. Fine. So what happens? Instead, if the electric field profile was initially like this, it becomes something like this, electric field versus say X. So it reduces due to the peak electric field reduces due to this lightly doped drain, and my hot carrier effects are what to say, we can deal with these hot carrier effects. And as it is a symmetric device, we do it in both the direction. So it becomes my n plus, and it becomes my n plus, and it is my n minus. Okay, and there are many interesting concepts, that why I am always drawing this as a straight line. What happens if it becomes something like this, or it becomes something like this metal oxide semiconductor? If there is some overlap, or there is some space between them, what will happen? There are so many interesting concepts to discuss. So I am thinking that end of the class, as I am supposed to take 2 hours of class, so at the end of the class daily I'll be taking small interesting topics, and I'll be talking with you. And in the meantime, if you have any questions, I'll be happy to happy to discuss on that also. Okay, so hope you guys enjoyed it, hope you guys liked the class, and hope the pace was not that much today. And if you want, you can check this link for previous classes lecture recorded sessions. I've shared it in the chat box, and if there is any question or any feedback, you can guys throw them at me. I'm ready to face them. So yes, floor to you guys now. Yes, 4049 SPK. Anyone can unmute yourself and you can say anything related to this topic. Any questions or anything? Oh, really glad to meet you. Yes, even I am very much delighted to meet you guys. So as I have few minutes left, you guys can even give a small introduction about yourselves, what you guys are doing, where you are doing. I hope you guys are doing bachelors at different premier institutes of the country. So if you want, you can give a short introduction of yourself. You can unmute yourself, or you can comment it also. I would like to know from you what you guys are doing. I wanted to become a VLSI design engineer, sir. Can you show some tips to know that, sir. Sure, 4049, you can unmute yourself and you can talk. Sure. See, analog and digital. Okay. See, digital is basically the jobs of digital, the jobs of analog are generally considered as much more. mu- uh, uh, the jobs of analog are considered as much more hardworking than digital. And even in my college, IIT Kanpur, uh, there is no professor who works on digital electronics. There are hardly few professors who works on digital electronics because most of the funding comes from analog circuits. Okay, because digital is something uh, which industry guys dwell more on, and analog is something which is both equally important in analog industry as well as academics. Okay, so there are few noted professors in different IITs who work on digital circuits, but analog circuits there are more number of professors because that domain the domain is such, the chance of optimization is much more than digital. So in terms of research, analog is better, but in terms of industry, both are present, but analog is generally considered as little bit more prestigious, you can say. Sure. See. The thing with digital is, I see that my transistors are scaling down, right? So what happens? Even digital and analog, they are kind of in terms of research. If you are doing masters, means basically you will be doing research there. Okay, at least for a year or a semester you will be doing research, and you are in premier institutes. You are expected to publish a good paper, a transaction, or a good conference, even in your masters. Okay, even my professor asks master students to publish at least one transaction or a conference. Good journals are called transactions. Okay, so digital is, the scope is good, very good, but analog is something that is really hard. Like we have master students who came for 2 years, but it has almost been 4 years, still they have not got their degrees because analog fabrication is really difficult. Even in digital, fabrication is really difficult. Okay, so it, you check the pros and cons and you decide which you want to go, because digital scope is there, but the scope is more on analog side, but at the same time they both require too much of intensive hard work and labor. Okay, and there is also this microelectronics part, the device part, where we divide more into device physics and all. There is scope of that also. There is new emerging technologies, like there is memories and all in which I work. There are something as neuromorphic computing and all, which are very hot topic right now. So there are many fields in VLSI. VLSI is not a small domain. It's really a huge and diverse domain. We deal from, say, we deal with device physics, we deal with quantum mechanics, we deal with circuits. Okay. Then some RF guys deal with this radio frequencies and all, signal processing and all. Then some of the guys deals with, who works in fabrication, deals with thermodynamics, heat transfer, charge, mass flow, everything. So VLSI is really vast, and all the fields have so much opportunity to provide to everyone who will be working in it. But what it requires is too much determination and hard work. So before coming to field like VLSI, you should be really passionate about your field. That is the main requirement and only requirement that I feel. Apart from that, you can choose any of the subdomains of VLSI. Okay. Yeah, most welcome. Yes, someone is saying he cannot unmute yourself. No, actually I have unmuted everyone, so you should be able to unmute. Yes, who is this speaking? Okay, Pavan, go ahead. Okay, 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 okay. Physical design, which one? Of one of the professor from IIT Roorkee. Is that the one? Okay, I got it. Got it. Okay, then. So you can contact me on LinkedIn. You can simply search my name and you can contact on LinkedIn. I'd be happy to help you. Okay. See, semiconductor industry is one of the industries which will not fall down. Okay. Even some of the fields, if it gets saturated like digital and analog, they will not saturate first of all. Okay. Even if they saturate, there are so many new domains that are emerging from semiconductor itself. Like, have you heard about 2D materials and 1D materials? Yes. So there is something as CNTs, carbon nanotubes, and all that are coming up. Then there is 2D materials like graphene or molybdenum disulfide, MOS2. Like VLSI is really progressing in multi directions, and which direction will survive or which direction will perish, when which new directions will come, it's very difficult to predict. But VLSI as a whole will always be there and it will thrive in the future. That we can say from the trends that we have been seeing. Okay. Okay. Any more? Anything else? Next Friday, 6 to 8. Hope the lecture was not boring, right? I tried my best to make it interesting. I hope it is not boring. Okay, Bharat. Yes, yes. Go. Okay. Okay, I'll be uploading the video. You can go and check it. You can go and check it on YouTube. Okay. Thank you. And Bharat, I think you were trying to say something. Yes, sir. Hello. Okay. 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 See, okay, see, like if I understand your question correctly, you are saying that you need concepts of ACDC as well, and you want some reference of some other courses. Is this what you are saying? Apart from VLSI, is this what you are saying? See, basically in VLSI domain, we need expertise of multiple domains. Okay, to work in this microelectronics and VLSI, this this whole branch. And see, when you are doing bachelor's, even in electronics and communication, what we do at second year and third year, we study the basic courses, right? The signal processing, be it electrical machines, AC analysis, DC analysis. We study these basic things, right? Once these courses are done, it is time for you to choose a branch if you want to work in industry or if you want to do some research in academics. Okay. So one you can choose is signal processing and signal processing. One you can choose is communication. Once you can choose is RF applications. Electrical person can go to power electronics or what it is called, grids and all, power transmission and all. Or you can choose microelectronics or you can choose VLSI. Microelectronics, VLSI are related with each other. Okay. So now see, for bachelor students, even I have done my bachelor's from NIT Agartala. in ECE. Okay, so my experience so far is the job roles of VLSI engineers uh, that they offer for bachelor student is mostly in the side of FPGAs. Okay, there will be some startups or some research institutes which will try to work on FPGAs, who try to implement something. They generally hire bachelor students. For going to like some companies like Intel or Qualcomm or Texas Instruments or Aura Semiconductors or Nvidia, there are many companies, okay, or TSMC. Generally they hire at least master students. That is what I have seen till now. Okay, they also hire bachelor students, but it's very few. Even in IIT Kanpur I am studying, most of my friends who generally goes to VLSI have at least done masters. Very few bachelor students have also gone. It's not like that they don't hire it, but at least you have to do a master for getting a good job role with a good, like very good, not decent, very good package. Okay, very good in the sense, in the range of around around 30 LPA, or if you do PhD then 50-60 LPS it might also go, but that is something of different. But for research oriented job roles in industry, master degree is generally something that is desired. For bachelors, you can, like as you said, you can focus on FPGAs and all, because even I have given interviews and I have cracked them. They generally work with FPGAs only, the research institutes, because working with this ICs and chips requires lots of investment. Okay, it requires around crores of investment, whereas in FPGA you can buy with 1.5 lakhs or 2 lakh rupees also. Okay, so this is something that you can keep your mind while selecting the next topics to work on, next courses to be taken before taking them. Okay, Bharat, it was nice talking with you. Anyone else? Okay, so if no one else is here, let us end this meeting today. See you next week from 6 to 8. So till then, happy learning, and see you guys. Bye. Okay.